Hey everyone, welcome to this explainer, cheerfully brought to you on behalf of Forge College. I'm absolutely thrilled to be your guide today. If you've been with us for a bit, you know we love taking these complex, kind of intimidating engineering concepts and breaking them down into beautifully simple, structured ideas. Today, we're tackling something every serious Web3 developer is going to face eventually: designing for high-frequency transactions. It's really the ultimate test of your code's resilience. Okay, let's dive into this.
Now check out this brilliant contrast. Over on the left, we've got this sleek, perfectly balanced single gear. That represents the incredible work you did in our previous lesson on resource optimization patterns for programs. You minimized account accesses, trimmed instruction data. Basically, you created a beautifully optimized program that runs a single transaction with absolute perfection. But here's the humorous, actually slightly terrifying reality check. What happens when 1 million users show up to turn that gear all at the exact same time? Well, suddenly you're dealing with the massive, jammed, grinding gear train you see on the right. This is the high-frequency reality.
Just to anchor us in our larger journey here, this explainer sits squarely within Mastering Program Architecture on Solana, which is a core module of the Advanced Solana Program Structures course. And why does this matter? Well, getting your code to work once, that's a basic skill. But hardening your code to survive real-world high-frequency traffic without just crumbling under the pressure, now, that is advanced architecture. This right here is the absolutely crucial step where you transform from a scriptwriter into a resilient systems engineer. So here's our engineering blueprint for today. We'll start with high-frequency chaos, then diagnosing bottlenecks, and the infamous write-lock traffic jam. After that, compute budgets, architectural fixes, and we'll wrap up with validating debug reports. All right, let's get into it.
Section 1. The high-frequency chaos. Let's see why transaction concurrency is basically just like urban traffic.
I really want you to think of transaction concurrency like urban planning. Imagine you build this beautifully paved one-lane bridge. It works perfectly when one single car drives over it, right? It's efficient, gets the job done. But route 10,000 cars onto that exact same one-lane bridge at rush hour, you get a catastrophic pileup. High-frequency transactions expose these totally invisible structural bottlenecks, which leads us to probably the most relatable mystery in systems engineering. Why did my beautifully optimized program just crash under load? It is so incredibly frustrating. You pack 2 fields into one account to save space. It was mathematically optimal for one user, but under stress, those exact micro-optimizations become severe contention points. Your optimizations actually built the bottleneck.
Moving on to Section 2. Diagnosing program bottlenecks. To fix our program, we've got to apply the scientific method. We can't just guess what went wrong here. We have to reproduce the failure locally. We do this by setting up a test validator and firing off a burst test to generate failures on purpose. Now, what's really interesting about this slide is how it maps those chaotic RKC errors in your terminal directly to their architectural culprits, so you know exactly what to look for. For instance, if your symptom is repeated account lock errors, your root cause is almost definitely write lock contention. If your symptom is a high proportion of compute budget exceeded errors, you've packed too many expensive calls together. Or if you see state inconsistencies, you've got non-atomic sequences that are assuming an orderly execution that just doesn't exist under heavy load. This diagnostic framework, it's literally your Rosetta Stone.
Section 3. The write-lock traffic jam. This right here is the absolute silent killer of scalability.
Let's zoom in on our working definition. Write-lock contention occurs when concurrent transactions fail because they're all competing to modify the exact same shared account. Think of it like this. Imagine a room with 500 people, and I ask all of them to write their name on a single piece of paper, but I only provide one pen. What happens? Chaos, right? People are waiting, they're fighting over the pen, and eventually the folks at the back of the line just give up and leave. That is exactly what the blockchain scheduler does when thousands of transactions target the same writable account. It serializes them, and if the line gets too long, it just drops the transactions entirely. Poof, gone. All right, Section 4, compute, budgets, and limits. The pen and paper analogy perfectly covers state, but what happens when you run out of processing power? A compute budget exceeded error is a transaction failure that happens when way too many instructions or particularly expensive cross-program invocations, known as CPIs, are packed into a single transaction. Remember how we said earlier optimizations can actually backfire? Well, if you decided to batch 5 updates into a single transaction just to save the user from signing multiple times, it works flawlessly for one user. But under concurrent load, the network's compute engine starts hitting its ceiling real fast. Suddenly, that clever little optimization blows up your compute budget, and the transaction gets completely rejected. No way around it. Section 5, Architectural Fixes and Sharding. We've diagnosed the illness, so now it's time to put on our city planner hats and prescribe the cure.
So the crucial point here is how we actually restructure the data. The most powerful tool we have in our arsenal is to shard state via PDAs, or program-derived addresses. Going back to our earlier analogy, sharding state means instead of giving 500 people one piece of paper and one pen, you give every single person their own piece of paper and their own pen. It's a total game changer. By deriving a per-request PDA, every transaction modifies a distinct account. The rate lock bottleneck is completely eliminated. Boom. Other fixes include serializing access through queues, splitting heavy instructions into lighter ones, or redesigning updates to be idempotent, meaning they can safely be retried without breaking the state.
Section 6, Validating with debug reports. Because a great engineer doesn't just guess that a fix worked, they prove it with concrete, measurable artifacts. Here's the exact programmatic checklist you need to follow to validate your architectural patches using your local test environment. Step 1. Run the burst test again with the exact same parameters. Step 2. Collect the RPC errors and program logs. Step 3. Run deterministic unit tests that specifically assert your state and variance haven't broken. And Step 4. Record the wall clock throughput. You're going to want to keep all these outputs time-stamped. This gives you empirical, undeniable evidence that your brilliant city planning actually fixed the traffic jam.
And this brilliantly illustrates our checkpoint requirement. For your optimizations to really be considered a success, you need to see a clear metric shift. We're talking at least a 30% reduction in the overall failure rate, or a doubling of sustained throughput. Seeing that massive drop in the failure rate proves that your sharding or instruction splitting didn't just theoretically help, it fundamentally improved the program's real-world performance under heavy load. That's what we want to see. Once you have all that juicy data, you document it so other engineers can reproduce your results. Your final artifact is a markdown debug report. It absolutely must contain a summary, your specific environment and commands, the observed failures from your baseline run, the root cause analysis, mapping those failures to the code, the specific fixes applied with code snippets, and finally, the indisputable before and after metrics. This report is the ultimate proof of your engineering rigor. It's the whole shebang. Now, building robust systems doesn't just stop here. Today's validation techniques actually act as the perfect foundation for what comes next. Up next in this curriculum is modular design and designing for auditability. In that lesson, you'll learn exactly how to structure your program modules to make these concurrency properties explicit in your interfaces. It's all about taking the hardened, stress-tested code you wrote today and organizing it so that auditors and fellow developers can instantly verify its safety. Before we wrap up, I want to leave you with this provocative thought. Are your optimizations ready for the million-user stampede? Because let's be real, in the fast-paced world of Web3, you literally never know when that stampede is going to arrive. Testing for high-frequency transactions isn't just a fun exercise, it's an absolute necessity for survival. I really hope this explainer has equipped you with the mental models and the practical steps to harden your architecture. Once again, this explainer was proudly made by Forge College. If you want to master more Web3 topics and continue building your engineering toolkit, please visit us at forge.college. Thank you so much for joining me today. Keep building, keep stress testing, and I'll see you in the next one.